Hello guys and welcome back to the Physics and Maths blog. Today we're going to go over concave spherical mirrors, the rules and focal points. So we're going to be discussing sign rules, what about concave spherical mirrors, and have an example, and then we'll move on to focal points at the end. So here are certain parts of a spherical mirror. As you can see on the right, there's a diagram of one, and we need to know these parts in order to answer questions later on and also for the sign rules. So the centre of curvature C is the centre of the sphere in which the mirror is a part of, which obviously makes a lot of sense, and so does the radius of the curvature, which is the radius of the sphere. The vertex, however, is the centre of the mirror surface, which is horizontal to the centre of curvature, and this is important, this vertex, to have because it comes in use when you're getting images from reflected objects, or also for the optic axis, which is the last part of the concave spherical mirror, which is a line passed through the centre of curvature and the vertex, and it is an axis of rotational symmetry. Moving on, we see that for the rules of spherical mirror, this is quite important because it allows you to get your answers right in questions or exams. So we need to get a general description for the mirror and lenses, and so we have three different criteria here. We have object distance, image distance, and rays of curvature. So your object is something that the rays are being produced from, these arbitrary rays, and which are being reflected or refracted. So when the object is on the same side as the reflecting and refracting surface as the incoming light, the object distance d0 is positive. So this means that your object, if it's producing light, it's on the same side as the mirror as the light that's going into being reflected, then it becomes positive. With image distance, is the image being created by the rays which are reflected or reflected. If it's on the same side as the outgoing light, so the reflected light then hits the image, then it's positive. If not, then it'll be a virtual image and it will be negative. And the same with radius of curvature. The center of the curvature C, if it's on the same side as the outgoing light, so the same side as the light that's being reflected or reflected from the surface, then it's positive. Now I'm going to show you an example which actually puts this to use. So let's look at this image here. We can see that we have a point P, which is our object, but it's a point object and it's on the optic axis. It's sending out a ray towards B at an angle of alpha above the optic axis. Now this ray strikes the mirror at B with an angle of theta, and due to the law of reflection we said in the last video, we know that it's reflected at theta back, and when it strikes the optic axis again, it's striking at P prime. Now we can use our sign rule, which we've just learned, to see that our d0, our outgoing ray, is on the same side as our object, and so it's positive. Our di, so our reflected ray, is on the same side as the image, and so that is positive, and our centre of curvature is also on the same side as the reflected ray, and so R is positive as well. So we see that all our signs are positive. Now, if we want to, let's say we want to find the distance of the image on the optic axis, there's a lot of math on this page. Pause it and have a look through, and it's quite easy to follow through. We can see that if we have these certain values, the di, d0, small sigma, and h, and we use all our angles, we can sort of eliminate through and use some simple trigonometry, which then cancels out due to the small angles, to find that if we know the object distance from the vertex and we know the radius of the sphere, we can then find the distance that the image will be away from the vertex. So this is I'd say pause and go through the math. I'm not going to explain it here, but it's quite easy to follow. And then this is just an example of finding the distance of the image. So now we're going to move on to focal length, which uses the equation we just found on this last page at the bottom, and says that the definition of the focal length is the point at which all parallel rays converge. So this means that our object, not our image, our object is sent towards an infinite distance away. So all the rays coming in are parallel to each other. So this can be seen on the figure on the right. Now taking the equation from the last page, setting the object distance to be infinite, and then letting our distance of our image be set to f to be our focal point, we can see that equation changes in order to see that the focal point is the radius over 2. So similarly, if we place the object at the focal point and then we say that the distance of the image is infinite, we can set d0 to be f and we get the equation there, and then eventually putting it all together we end up getting this very important equation called the mirror equation, which says 1 over the distance of the object plus 1 over the distance of the image equals 1 over the focal point. And that is a very important equation. I'd say definitely try and remember that. So that comes to the end of the video. I hope this all made sense. It's just an introduction to concave spherical mirrors and focal points. I hope the math wasn't too difficult. Make sure you hit like and subscribe. Comment any videos you'd like to see, and I hope this series of optics is understandable and it's interesting. Thank you guys for watching. I'll see you guys in the next video. Goodbye.